Hello everyone. Today we're going to learn harmonically excited vibration, part 1. The learning objectives. After completing this topic, you should be able to do the following. Find the responses of undamped and viscously damped single degree of freedom systems subject to different types of harmonic force, including basic excitation and rotating unbalance. Distinguish between transient, steady state, and total solutions. Understand the variations of a magnification factor and phase angles with the frequency of excitation and the phenomenon of resonance and beats. Derive transfer functions of systems governed by linear differential equations with constant coefficients. Solve harmonically excited single degree of freedom vibration problems using Laplace transform. Solve harmonically excited vibration response using MATLAB. Introduction. The first is the definition of a forced vibration. A mechanical or structural system is said to undergo forced vibration when external energy is supplied to the system during vibration. The external energy can be supplied through either an applied force or an imposed displacement excitation. The applied force or displacement excitation may be harmonic, non-harmonic but periodic, non-periodic, or random in nature. The response of a system to a harmonic excitation is called a harmonic response. The non-periodic excitation may have a long or short duration. The response of a dynamic system to sudden applied non-periodic excitations is called a transient response. Let's start by looking at this general spring mass damper system, where a force is applied on this mass, which is Ft. We already learned the equation of motion of this system can be obtained by using the Newton's second law. Before writing the equation, we need to do the force analysis. The mass m is subject to three forces: the spring force kx and the damper force c times x dot, and also the externally applied force Ft. Since we already know that the gravitational force will be cancelled out by the static deflection, so that's not considered in the force analysis. So we can write the equation of motion as mx double dot plus cx dot plus kx that is equal to Ft. Since this equation is non-homogeneous, the total solution xt that is equal to xht plus xpt. xht that is the homogeneous solution and xpt that is the particular solution. Let's look at the time response of these two solutions. The first part is the homogeneous solution. We know that the homogeneous solution is a solution to the associated homogeneous equation mx double dot plus cx plus kx that is equal to 0, which is also related to the free damped vibration. We already know that if the damping constant is between 0 and 1, this is the response that we will see. So over time, the magnitude will die out. The particular solution is caused by the external excitation. It will have the same frequency as the externally applied force. And the total solution will be the summation of the two, which will give us a response like this in the solid line. Let's look at the simplified system where the damper is not considered. Let's consider this undamped system subject to a harmonic force, Ft that is equal to F0 times cosine omega t. We can find the equation of motion from Newton's second law as mx double dot plus kx that is equal to Ft. Since this equation is non-homogeneous, the total response xt that will be equal to xht plus xpt, where xht is a homogeneous solution xpt and xpt is a non-homogeneous solution. The homogeneous solution xht is a solution to the function mx double dot plus kx is equal to 0. We know that xt will be c1 times cosine omega nt plus c2 times sine omega nt, where omega n is a natural frequency, which can be calculated by using square root of k over m. Because the exciting force Ft is harmonic, the particular solution is also harmonic and has the same frequency. Thus, we can assume a solution in the form xpt that is equal to capital X times cosine omega t, where x is a constant that denotes the maximum amplitude. By substituting xpt into the equation of motion, we can solve for x. So we have mxpt double dot plus kxpt that is equal to f0 times cosine omega t. So we can solve for the capital X. So the capital X becomes f0 over k minus m omega square. We can further divide k on both the numerator and the denominator, and the numerator becomes f0 over k. We can further define f0 over k as a static deflection delta st, so the numerator becomes delta st. The denominator, since we divided by k, so it becomes 1 minus m over k times omega square. M over k, that is 1 over omega n square. So the final solution becomes delta st over 1 minus omega over omega n square. Using the initial condition x at time 0 is equal to x0, x dot at time 0 that is equal to x dot 0, we can find that c1 that is equal to x0 minus f0 over k minus m omega square, c2 that is equal to x dot 0 over omega n. So putting all these constants together, we can find the total response xt that is equal to c1 times cosine omega nt plus c2 times sine omega nt plus x times cosine omega t. Let's look at how the magnitude of the particular response changes as the omega changes. Here we have a definition of a magnification factor, or we can also call it amplification factor or amplitude ratio. The amplitude ratio is defined as x over delta st. From the above equation, we can find that it is equal to 1 over 1 minus omega over omega n squared. And there are three different cases. The first case is when omega over omega n that is less than 1. When omega is equal to 0, we can find from this formula that x over delta st that become 1, which represents this point over here. As omega increases from 0 but below 1, we can see that this term will increase. This is why 1 minus omega over omega n will decrease. The invert of that, which is x over delta st, will increase. So this is why we see on this curve, as omega over omega n increases towards 1, and we will see the amplitude ratio keep increasing. And we also know that it's a positive number as long as omega over omega n that is less than 1. And we also know that when omega get very close to omega n, the ratio of them become almost 1, and 1 minus that becomes almost 0. So this is why x over delta st will approach infinity. We can also represent by looking at the time response. So if we have the force giving this curve, then this will be the final response. The second case is when omega over omega n that is greater than 1. Look at the term again. If omega is greater than omega n, it means this term is greater than 1. So x over delta st that become a negative number. So it will be always a negative number. We also know that if omega that is very close to omega n, but greater than that, this 1 minus a number that is slightly greater than 1, which is almost close to 0 but a negative number, we know that x over delta st become negative infinity. So it will be some point far away from here but close to negative infinity. As omega keep increasing, and this number will decrease. So this is what we see in this plot. It will decrease. And if omega is almost close to positive infinity, or the ratio that is very large, in that case, the number becomes almost 0. The case 3 is when omega over omega n that is equal to 1. This is also a case called a resonance. So since we know that a vibration due to excitation will become infinity eventually, let's see how it is built up by starting with 0 initial condition. We can rewrite the total response by keeping the initial condition terms together and everything else related to the external force together. So we have x0 times cosine omega nt plus x0 dot over sine omega t, and the rest will be kept together, so it becomes f over k minus m omega squared times cosine omega t minus sine omega nt. And we can further write it in terms of static deflection. Then it becomes x0 times cosine omega nt plus x dot 0 over omega n times sine omega nt plus delta st times cosine omega t minus cosine omega nt over 1 minus omega over omega n squared. And when omega gets very close to omega n, we know that we cannot find the limit directly of the last term. So we can apply L'Hospital's rule to evaluate the limit of the last term, which tells us that when omega gets close to omega n, this term will be the same as the limit of omega close to omega n, the time derivative of both the numerator and the denominator. By taking derivative on the first term, it becomes t times sine omega t, and at the bottom becomes 2 omega over omega n squared. Take the limit calculation, it becomes omega n times t over 2 times sine omega nt. And we can put this together to find the response xt, that is equal to x0 times cosine omega nt plus x dot 0 over omega n times sine omega nt plus delta st times omega nt over 2 times sine omega nt. And if the initial conditions are 0, say x0 is 0, x0 dot is equal to 0, the two terms will be gone. And the last term, we can see that it is a sine function with a frequency of omega n. But the magnitude is a function of a time t. So it implies the magnitude will keep increasing. So this is what we see from the plot. Over the time, the magnitude of the vibration will keep increasing. And we also know that all these three terms, they have the same frequency. So it means they are synchronized harmonic motion. The summation of them will be also harmonic motion, but with a different phase angle. If we plot that out by using the time domain curves, you will have a similar shape, but started with a different phase angle. Let's look at the total response of the system in time domain. We copied the solution we had before. So for the first case, when omega over omega n that is less than 1, we know that the first two terms, that will be the vibration with the frequency of omega n. The last term will be the vibration with omega. Omega is very small, so this is why we will see this type of vibration. It has a vibration with the frequency of omega n, but at the same time, on the larger scale, the whole thing vibrates with another frequency of omega. This is why the period of this vibration becomes 2 pi over omega. This is also something as what we did before about the result of a summation of two harmonic motions with different frequency. The second case is when omega over omega n that is greater than 1. So it means that the external force caused vibration will vibrate at a higher frequency, which is what we see from this solid line over here. But at the same time, it vibrates with another frequency of omega n, where omega n is much smaller. So this is what we see as a time domain response. So we have discussed what happens when omega over omega n that is equal to 1. Let's see what happens if omega over omega n that is approximately 1. If the forcing frequency is close to, but not exactly equal to, the natural frequency of the system, a phenomenon known as beating may occur. Again, we're going to start with the total response of the system. To simplify the discussion, we'll assume the initial conditions are 0. So we can write the total response xt in this form. And over here, since the two frequencies are very close to each other, we'll define omega n minus omega as 2 zeta, and omega n plus omega become 2 times omega. We can derive omega n squared minus omega squared, that becomes the multiplication of the two terms, which is 4 times zeta times omega. We can plug these numbers back into the total response equation over here. Then we can find the total response xt, that becomes f0 over m over 2 times eta omega times sine eta t. Sine eta t is from this term over here, times sine omega t, which is this term. By looking at the result, we can see that this vibration will include a sinusoidal vibration, sine omega t. At the same time, the magnitude of this vibration is another sine function, sine eta t. Since eta is very small, we'll know that the vibration will look like this, the solid line. And the dashed line describes the magnitude of this sine wave, which is the sine eta t, with the coefficient of f0 over m over 2 times eta times omega.